All right, I didn't receive any questions last 24 hours, so any questions you got, put them up in the chat. Otherwise, I'm just kind of here. DG from an equilibrium constant problem. Okay, so I'll bring up one of the problems in the packets. So in these types of problems, spin for you just a little bit there. So we can, these are basically solved the same as the ones beneath them. So we've got the delta G naught and KQ, and beneath it the delta G naught, KQ from delta G naught. The relationship we're going to work with here is that delta G naught equals minus RT ln of KEQ. And then if we just rearrange this, we get KEQ equals E to the minus delta G naught over RT. R in this case is 0.008314. The temperature here is going to be whatever temperature we're given in centigrade, convert it to Kelvin, because we do have gas constant R. So these are all done at 25 degrees C, so they're all going to be done at 298 Kelvin. So let me bring you back to desktop. So once new delta G, just minus R, 8314, times the temperature, 298, times the natural log of our KQ, 1.30, e to the negative 33. So in this case, our delta G is 187, 188. For the ones beneath it, we're asking you to find KQ from delta G naught. KQ is E to the negative delta G naught, 141 in this case, divided by the ideal gas constant, 0.008314, times the temperature in Kelvin, 298 Kelvin. We close that out, we're going to get 1.93 times 10 to the negative 25. Now, in terms of what's considered a reasonable answer, so if you're looking for a way to kind of verify that your answer is correct, Delta G is going to typically sit between 25, 200-ish. That's not a hard range. You can be definitely less than 25, practically over 150. But again, that's going to be a more reasonable answer. You should be guessing like 0.1, and you should be getting something like 10,000. The KQs, those are all over the place. They span a whole bunch of orders of magnitude just because they are a complicated function of concentration. So typically, if your delta G is positive, you should expect some teeny tiny numbers, so 10 to the negative 2 and smaller, but in this case, you can see down 10 to the negative 33. If your delta G is negative, your KQ is going to sit like tens, hundreds, thousands. Typically, we don't get a KQ near 1, simply because it implies a reaction where the forward and reverse reactions are equally favorable, and that typically doesn't happen. But yeah, that's how you approach these problems. You just got the two relationships. Delta G naught equals minus RT KQ. You can rearrange this, divide the negative RT, and then take the exponential, and you'll get the other relationship. Adjust one of my lights real quick. So typically when we write any type of, so the question here is, could you write how HCO2 behaves in water? So typically we don't assume the water is going to contribute the acid source. So the water here is always going to be H2O. So we HCO 2 negative. So in this case, we're going to treat the acid as losing a hydrogen. This is CO2 minus 2 plus H3O plus. But rarely do we ever treat the H2O as having an H plus. Also, the way to our credit, there is a way that we try to write this, and the way we try to write this is with the leading hydrogens forward. Let me bring up the buffer boot camp just to make sure what I'm telling you is correct. For those of you curious, Buffer Boot Camp's not due till like next month, so if you're not on it, that's perfectly fine. This is actually the next test material. Yeah, I think it's a randomized algorithm, so I'm not seeing the HCHO2 minus. I'm guessing that's supposed to be HCO3 minus. But again, it should follow the behavior I've got written up on the board. It's going to lose a hydrogen to give you the H2O plus and the CO2 minus. We never write this as being H3O plus. The H3O plus is always going to be on the right side. It's acting like an acid. And if it's going to be a base, we're going to write the OH minus on the right. Because the concentration of H plus and OH minus are so small in water, we typically treat them as non-existent. You're welcome. Other questions? I prefer you would transcribe them all by hand. I mean, if you print, honestly, if you print them in, I'm probably not going to take off any points, but it's really not. If we were in a student lab class, yes, I would most definitely tell you need to like transcribe these tables by hand. So I think you got the time, you do need to write them out. I mean, I say should as saying someone who kept a lab notebook for years and like, yeah, people weren't going to get upset if you print something out. But for completeness, you should be doing everything by hand. So K is just another equilibrium constant. So within the equilibrium constants, so EQ is just an equilibrium constant. And it doesn't really specify what type of equilibrium, it just says that we have an equilibrium. So within the KQ family umbrella of equilibrium constants, there are several subsets. So a Ka refers to the equilibrium of a weak acid. And this is going to come a lot more for the test 4 material, so this is just kind of laying the groundwork, so this way it's a little bit easier to go through that. But when we have Ka, we're specifically looking at a reaction that looks like this. So we have something losing a hydrogen and giving us an H plus and a cation. Some books will write it as HA plus H2O, goes back and forth to H3O plus A minus. These are equivalent statements. There's Kb, which is just a weak base. It is akin to this, meaning that with a weak base, we're always accepting a hydrogen or forming an OH minus. So we'll talk about that more when we get to the next test, where there's the Arrhenius definition of bases versus the Bronsted definition of bases. But the Kb here is always going to refer to Kb to a base. KSP is the solubility product. And basically the solubility product is the equilibrium constant for an insoluble salt dissociating in water completely. So if you have something like calcium phosphate, the KSP is for 3 calcium cations plus 2 phosphate anions. And the last one, Kw, is the dissociation constant for water. So when we go to solve an equilibrium problem, if you're given Ka, Kb, Ksp, Kw, Kq, these are all an equilibrium constant. They're all a Kq, they're just a specific case. So for the problem we solved, using a quadratic. So typically what you'll get, let's say we have H2CO3 dissociating into H plus and HCO3 minus 1. And there is some Ka associated with this, but we're not going to worry with the number. And we've got some starting concentration of H2CO3. Let's say that's 1 molar. And let's say we've got some starting concentration sodium bicarbonate as 1 molar, and we want to know what the concentration of H plus is. In this case, we would have our Ka equals Q, which equals the concentration of HCO3 minus 1, concentration of H plus, all over H2CO3. We build our IC table. So we have H2CO3, H plus, and HCO3 minus 1. Our H2CO3 concentration is 1 molar. H plus is 0 because we're not given it. In HCO3, the sodium here is just a spectator. So this ends up being 1 molar. Change is minus X. x, and x. So we get 1 minus x, and 1 plus x. We want to know the concentration of H plus. This is the square we're solving for. So we'll stick this back in and we get this as x times 1 plus x all over 1 minus x. What we do with the Ka at this point, I'm going to have to erase the IC table just because I don't have space on this board, is we treat it as a variable in our quadratic equation until we're ready to solve. So if you rearrange this, we get Ka times 1 minus x equals x plus x squared. If we distribute the x's over, rearrange, we get 0 equals x squared plus 1 plus Kax minus Ka. So this is just algebraic rearrangement of this equation. If we use the quadratic, off x squared plus beta x, ax squared plus bx plus c, we get that x equals the opposite of b, in this case 1 plus Ka, plus or minus the square root of 1 plus Ka squared minus 4 times a, which is 1, times c, which is minus Ka, all over 2 times a, which is 1. So the way you would use your Ka in this case is that it's just a number that gets plugged into your quadratic equation. So if we know the Ka of this reaction, it just ends up getting dropped into 1 plus whatever that number is, plus minus square root of 1 plus that number squared, minus 4 times that number, all over 2. Now again, Ka and Keq are synonymous. So a Ka is just an equilibrium expression. It's a specific type of equilibrium. It's a weak acid dissociation, but it's still a Keq. All right, one of the problems from the pressure dependence homework. So the pressure dependence is basically saying, if we have changed the pressure, how does it affect Q? So this is one of the first problems. What is the pressure dependence? P to the n of the following reaction. So the way the big picture on how we solve these types of problems is that, oh, you're welcome. If we write an expression for Q, so far we've just written it out as concentrations. So let's look at, that would have been the water gas shift reaction. There's some flavors over it. H2, gas goes back in plus CO2, goes back and forth to H2O gas plus CO gas. So Q for this reaction, concentration of H2O, concentration of CO, over the concentration of H2 times the concentration of CO2. Now, we can use the ideal gas law to rearrange to solve for concentration. So the ideal gas law says that pressure of I equals the moles of I times nRT. If we rearrange, we get pressure over RT equals moles over volume, which is molarity, but we don't measure partial pressure in reactor, we measure the total pressure. So we need to make the substitution X of I, and P0 here is your total pressure. So if we make this substitution for every gas in this equation, we will end up with mole fractions, and we'll end up with some powers of P naught over RT. What it's asking for is, okay, if you were to make this substitution in for H2O, CO2, H2O, and CO, what value do you get for PO? What's it raised to? What's the order of pressure? So one option is to make this substitution every time. The other option is that there's a shortcut. And the shortcut says that the pressure dependence equals the moles of product gases minus the moles of reactant gases. So if we look at the reaction, and again, I'll bring it back up on the screen so it should be a little bit clearer. Here we have 1 mole of gas here and 1 mole of gas here, so that's 2 moles of gas. For product gases, for our reactant gases, we have 1 here, 1 here, so that's 2. 2 minus 2 is 0, so our pressure dependence in this case would be 0. For the next one, we have 2 moles of gas product. We have 1 plus 3, 4 moles of gas reactant. So 2 minus 4 will give us this -2. And for this one, we have 0 moles of gas on the product side, and we've only got 1 mole of gas on the reactant side. So 0 minus 1 is your -1 pressure dependence. The implications of this is that if something has a positive pressure dependence, it means that Q will increase as we increase pressure, which means the reaction will go backwards. If we have a negative pressure dependence, if we increase the pressure, Q goes down, so it actually drives the reaction in the forward direction. Someone's asked about the crossover temperature. Yes, it is actually that easy. So to figure out the crossover temperature, what the crossover temperature represents is when a reaction switches between spontaneous and non-spontaneous. So when delta G switches between positive and negative, and there's only one number where that occurs, which is 0. So our relationship is delta G equals delta H minus T delta S. So at the crossover temperature, at CO, delta G is 0, meaning that we're neither favoring nor not favoring this reaction. So we rearrange, we get 0 equals delta H minus T delta S, or the T at the crossover temperature is just delta H over delta S. Now, a common mistake here, delta S is still in joules per mole Kelvin, so you had to make that conversion from joules to kilojoules. Once you made that conversion, your temperature is in Kelvin. You can be asked for centigrade. Your answer is still right in Kelvin. It's just kind of making sure that you recognize the temperature you're getting here is Kelvin. Right? You're welcome, Catalina. But yeah, it's just delta H over delta S with delta S in the correct units. That'll get you the crossover temperature in Kelvin, and then if you're asked for centigrade, which I typically ask for just to make sure you're paying attention, you just subtract off the 273. Yeah, you're welcome. Yeah, crossover temperature is super easy. There should definitely be a question getting right on the next exam. Other questions? Oh, Le Chatelier's actually is pretty, yeah. Le Chatelier's. So there's 3 forms of Le Chat. Concentration, pressure, and temperature. So concentration is the easiest to understand. And the idea with concentration is that let's say we have an equilibrium. We have the equilibrium condition, KQ equals Q, and Q here is a function of concentration, specifically the products over the reactants. Now this is a ratio. If we change this ratio, if Q is greater than KQ, we've got too many products, and so we'll drive the reverse. What will happen is the reaction will react away the products because it's a reversible reaction, and we'll start creating more reactants. Conversely, if Q is less than KQ, we drive it forward. So if the concentration is the easiest to find, because easiest to understand because it's the one we're controlling directly. So if we add products or remove reactants, either one will make this ratio too big, we drive the reverse reaction. So adding products or removing reactants causes it to go backwards. Conversely, if we add reactants or remove products, because again, that's going to change this ratio, Q will be less than KQ and will drive the forward reaction. Now, pressure, this is where your pressure dependence comes in. What Lechat says about pressure is that if we increase or decrease pressure, the reaction wants to go back to the pressure it was at. So if we increase pressure, we favor the side with less moles of gas. If we decrease pressure, we favor the side with more moles of gas. So hopefully that was one of the ones you're asking about. The shots. So yeah, luckily that's one of the ones you're asking about. So in this case, we're going to increase the pressure. Well, to compensate, it wants to go to a side with less moles of gas. So if we look at the right side, we've got 1 mole of gas. On the left side, we don't have any. So it's going to go to the side with less moles of gas, which will be the left side. So in this case, we're going to make more calcium carbonate because we're driving the reverse reaction. Now, that said, if we look at something like the water-gas shift reaction, so let me bring that reaction back up. So if you look at this reaction, it has 0 pressure dependence, meaning that there's not more moles of gas on one side or the other. So we've got 2 moles here and 2 moles here. If we increase the pressure on this one, nothing's going to happen because there's no way for the reaction to relieve the pressure. So the more complicated part about the pressure dependence is that you're going to have to look at the reaction and see if there's more moles of gas on one side or the other. If there isn't, meaning there's the same number of moles, there's no effect on pressure. If there is more moles of gas on one side or the other, if we increase in pressure, it's going to go to the side with less moles of gas. Now, the temperature is easy in the sense that it always does the same thing, but hard in the sense that you can't look at a reaction and know. So the idea with the temperature is that if we increase temperature, the reaction is going to want to cool back down. And to do that, we're going to favor the endothermic direction. Conversely, if we decrease the temperature, we're going to favor the exothermic. So if it cools down, it's going to release heat to get the temperature back up. If we heat it up, it's going to do the endothermic direction to cool back down. The problem is that you can't look at a reaction and know that. So you have to be told if a reaction is endothermic and exothermic. And when we say if a reaction is endothermic or exothermic, we're saying about the forward direction. It's implied the reverse direction is going to be the opposite. So if we go back to, I'm assuming that's the next question. Ooh, actually I don't have any Lechat layers on those. But basically that would be the solution. Like if you see that, if I say we're going to heat up an endothermic reaction, well, it's going to go forward. If we heat up an exothermic reaction, it's going to go backwards. Now your question was about the other one, number 3. What would happen if SO3 minus was removed from the reaction using strontium plus 2? So what the strontium plus 2 does is that it removes this SO3 minus 2 as strontium sulfite. It's an insoluble ion. So what you're doing here is selectively decreasing the concentration of SO3 minus 2. So this is the relevant part. SO3 minus 2 was removed. If we remove it, we're decreasing the concentration of the products. So we're removing products. This makes Q less than KQ. So this is going to drive the forward reaction. And the answer, as you saw, this would make more calcium sulfite dissolve. Because, the sulfite's too small, we have to dissolve more of the calcium sulfite to get its concentration back up. Yes, you're very welcome. Now, just a reminder, the exam does open up tomorrow. Traditionally, during the normal seated summer semester, we would have been taking the exam this Thursday. So that's part of the reason why we're taking it when we are. The second is to give you those couple extra days. The last two exams started on a Monday and finished on a Friday. This is going to start tomorrow on a Wednesday and finish up next Tuesday at midnight. So you actually get the additional 2 days. Hopefully a lot of you are catching on to this. The discussion boards are very useful. The homeworks are very useful. The study packets are very useful for seeing what's going to be on there. Again, I'm not trying to give you any gotcha questions. The discussion boards are meant to represent the harder problems are going to be the exam, so this way I at least know that you saw them, or at least saw some exposure to them. But definitely the discussion board that pops up tomorrow is going to be another type of question you can be asked on the exam. Again, the exam opens up tomorrow. We would be taking the exam Thursday, which is why the homework is due tomorrow night. But for those who are feeling comfortable with the material, you can go ahead and start tomorrow if you want. But again, you get a full week to take this exam. It is the hardest exam you're going to take. The next one is actually much easier. It's kind of building off the concepts we're doing right now. So if you can do this test just fine, the next exam is substantially easier. But I also kind of like to get this exam out of the way before the withdrawal date during a regular semester, just so students kind of know what they have going into test 4 and the final. But do not feel that you need to take the exam tomorrow. Like, definitely do the discussion board, and if you're feeling comfortable with the 3 discussion boards we have, the thermo, the solvent equilibrium, and tomorrow's going to be the free energy change, the delta G, not the delta G naught, but the delta G based off of Q. That's a big chunk of the exam right there. And yes, fair warning, there is a long Hess's law problem at the end of the exam. If I remember correctly, this exam only has like 14 questions on it. There are only 13 questions on this exam. Correct. If we add reactants, it's going to drive the forward. If we add products, it drives the reverse. If we remove reactants, it drives the reverse. And if we remove products, it drives the forward. Again, it boils down to that ratio of Q. Q is a ratio of products or reactants. If Q is greater than KQ, then we go in the reverse direction. If Q is less than KQ, we go in the forward direction. So we can change that ratio 2 ways. We can change the numerator, which is the concentration of products, or we can change the denominator, which is the concentration of the reactants. Either one will have the same, they will have analogous effects. You're welcome. Other questions? All right, I'll give it about another 8 minutes. Let's get to about 11:20, and then if no one's got any questions, we'll just head out from there. when the free energy changes versus Q problems in the homework. So with these types of problems, this is the non-equilibrium condition. Honestly, these are the much easier problems to solve. And the trick with these problems is read what the problem is asking you for. We talk a lot about solving for the equilibrium conditions, but this is one of the few times we were not at equilibrium. So when we are not at equilibrium, we can use the following relationship. So for a non-equilibrium reaction, meaning that Q does not equal KEQ, we have some leftover free energy, and this free energy describes whether or not the reaction will go forward or backwards. Basically, if Q is greater than KEQ, meaning that we've got too many products, the delta G will be positive. If the Q is less than KEQ, the delta G will be negative. It just says it's another way of retelling the Chatelier's principle. Based on the Q, which way should the reaction go? And the homework is set up to kind of help you through this type of problem. So the first thing this problem asks you for number one is, what is Q? So you've got your reaction calcium phosphate dissociating into calcium and phosphate. So you still need to describe Q, and Q in this case equals the concentration of phosphate to the second power times the concentration of calcium to the third power. So where do you get these concentrations from? Well, it gives it to you in the problem statement. So if we go to the problem, it tells you the concentration of calcium here is 0.2 molar. And the concentration of phosphate is 0.4 molar. And if we put this into that equation and we solve it, we're going to end up getting 0.00128. The next step then is just to plug in the values into this relationship. So we know Q is 0.00128. We're given the temperature in this problem as 75 degrees C. So this needs to be to convert it to adding 273 to 348 Kelvin. R is your 0.008314, and the free energy change delta G naught is given to you as 164 kilojoules per mole. So you take your 164, add 0.008314 times 348. I'm assuming that's what 75 plus 273 is. Take the ln of whatever number you get for Q. And in the case of this problem, when you work it out, what you'll get is that the delta G is 145. Now, a few notes on this. It takes a lot to radically shift delta G. So going from 164 to 145, that's a pretty reasonable shift. You're generally not going to see it shift more than like 50 to 75 kilojoules per mole. So it takes a lot, and we'll talk about when we start talking about batteries. This relationship will come back again, but again, you should be getting something akin to what you started with. But that's all you do for those types of problems. You calculate Q, and you plug into this relationship. Now, notice it's not asking you for the equilibrium concentration. That's a common mistake I see. Students try to go out and they try to solve for equilibrium concentrations. It's not telling you, it's not asking you for the equilibrium. If you look at the wording of the question, it says, for the following reaction, what is Q, what is delta G? It's not asking for the equilibrium, it's asking you what is Q based on these numbers and what is the delta G based on these numbers. Now, at equilibrium, so if Q did equals KQ, we would get that this equals 0. So if you don't get 0, it's simply due to rounding errors more than anything else. So to ask you what delta G is at equilibrium, the answer is automatically 0. And to ask you what Q is, well, it's KQ. So these types of problems are not asking for equilibrium concentrations. They're asking you for the non-equilibrium cases. So this is what makes these pretty simple problems, is that you just kind of use the numbers that you're given. Other questions? there aren't any other questions, again, just a fair reminder, the exam opens up tomorrow, but you have until Tuesday of next week to take it. So make sure you can do the discussion board tomorrow and the other two discussion board questions. Look through the homeworks and also look through the online packets. The online packet's going to have a lot more for you to work with in terms of finding the Hess's Law problems. There is going to be a big Hess's Law problem on this exam, so make sure that you are comfortable with solving those types of problems. Other than that, I will see you all tomorrow. Thanks to all of you who were able to show up today.